Hey everyone, hope you're all doing well. So DeepSeek has been causing quite the stir worldwide, both in the AI community as well as stock market and in many other places. So last week I had explored DeepSeek in one of those videos wherein I had shown how DeepSeek was explaining computer vision concepts. So here is the video that I had just explained. Deepseek R1 explains advanced computer vision concepts, right? So what I did was, this was from my own kind of like experience, is that I used to watch this lecture, and in order to find out what the solution was, I had to go back and refer. So I was trying to see if thinking models like DeepSeek or even other models like the O1, OpenAI O1, or even Google's Flash thinking models, if these can be helpful as a real-time, like an AI teaching assistant, an AI TA, or something like that. And so what I did was I took a screenshot of this and sent it back, and then we saw that DeepSeek was doing a great job, and that it was able to, just from a single screenshot, it was able to completely get what the whole context was and what the whole algorithms were, and so on. And it even gave out the Python code for that. So it's like just from equations, it was able to know what the concept was, and then it also generated the Python code for that, right? So and this could be helpful in scenarios where, say, if most of us watch video lectures and we don't have direct access to the professor or the TA right away, and AI could come in, thinking models could come in and act as almost like a real-time teaching assistant to clear doubts and or even bounce back the concepts and so on, right? So this time I wanted to do something the other way around, in that so previously I used to do is that I had like an O1 decode math from a Python screenshot. So this time it's the other way around, right? So this is a code snippet of Professor Hani Farid, who is teaching a lecture on linear regression with stochastic gradient descent optimization. And so here you have the Python code, and you don't know what the concepts are except for maybe some comments here and there. So we want to see if also like if how the image understanding is, and if AI could do the reverse from the code, it can get the concept. Last week what I did was from the concept get the code, and here we're going to do the reverse, right? So so OpenAI did a good job. OpenAI O1, I did this a while back, and this did a good job, and I also wrote a blog on this and had also done a couple of videos on this. And I'd also done the same thing with Google's Gemini Flash thinking model. So that also did a good job. It was able to like decode the math from just a Python screenshot. So I had written that, okay, both O1 and Flash both were impressive. So it was able to get the correct context and do it. So this time I wanted to do the same thing with DeepSeek, because DeepSeek R1, because so DeepSeek R1 is a little different, right? Like from the previous two thinking models, it has caught the like the imagination of so many people, AI enthusiasts and others as well. Is that it gives you a real-time thinking of what it's doing. So that's like really kind of there. Actually, even Gemini was doing that, but not to the level of detail in which DeepSeek was doing. So what I want to do is that I'm going to like kind of upload the same image that I showed right now, the same image which I had uploaded to the O1 as well as the Google Gemini. And I'm going to send that to DeepSeek, and let's see what DeepSeek is able to say. And I'm going to send the same prompt just so that we're all three models are compared same in a similar way. So I'm going to click on Deep Think. So Deep Think is what actually like will enable the thinking model of DeepSeek. And this is going to be the image that I'm going to send. So this is a screenshot with the Python code, which of Professor Hani Farid's lecture on stochastic gradient descent optimization. So let's see what Deepseek is going to say when I upload this particular picture, right? And once I upload this picture, what I'm going to do is that I'm going to say that this is a screenshot of a lecture by Professor Hani Farid from UC Berkeley. Can you extract the text from the screenshot? Can you explain to me what concept he's teaching based on the text and code you extract? So one thing you have to remember here is that this is not an image model. Like this is not. This is just it only extracts text from images and files, right? So this is not like a vision model like the other possibly the other ones. So that's something that we have to keep in mind. So again, this is the image that I'm going to send. And let's go right in and see what Deepseek is going to say when I'm uploading a Python screenshot from a math lecture, machine learning math. So you can see the thinking that's going on. So thinking, okay, let me try to figure this out. The user provided a screenshot of a lecture by Professor Hani Farid. So it's going on. I don't want to disturb its sequence. So let's see. It's amazing. I think that's one of the main differences of Deepseek from other models is that the way it thinks and the way it reasons with itself. That's something which a lot of people really caught the attention. Kind of. So if you can see here, okay, let me try to figure this out. The user provided a screenshot of a lecture by Professor Hani Farid with some Python code. They want me to extract the text from the code and explain the concept being taught. First, I look at the code provided. The code starts by importing NumPy and matplotlib, which are common numerical computations and plotting. So it even starts by okay, what the import functions are. And then there's a section called model. So this is actually a comment. Here they're generating a random slope and intercept, so it's just at 6 NP, so it's also able to get that this is actually a random value, kind of. The X values are created from -1 to 1 with steps of 0.1 reshaped into a 20 by 1 array. The Y values are calculated as U0 X plus U1, which looks like a linear model. That is absolutely right. It's amazing how it's able to break these step by step. Then they stack a column of 1s to X, probably to create a design matrix for linear regression. That is absolutely correct. Because this is you have two equations, right? It's a linear equation, right? So you have to have a columns full of ones to map this is going to be the other column. So next, under quadratic form, they compute so this is the next section which says quadratic form. They compute A equals X transpose X plus and B equals X transpose Y. This is part of the normal equation for linear regression. That is also correct. This is the basic normal equation. A is the transpose of the design matrix multiplied by itself, and B is the transpose of X multiplied by Y. So this is how you kind of for linear regression, when you have the measurements, this is how you kind of design the matrix. And the normal equation solution would be the linear the NP dot linear algebra of inverse, basically the pseudo inverse, but that's not in the code here. That is interesting. So what he's saying is that the solution would have been the pseudo inverse. It's not mentioning the name pseudo inverse, but that's what this kind of this is actually just the inverse, not even the pseudo inverse. U equals A inverse B, but that's not in the code here. Then comes the steepest descent section. Steepest descent is an optimization algorithm used to minimize a function. So then it's just they initialize UI with random values -5 to 5. And then they start a loop. So it's able to decipher the residual Ri equals B minus AUI, which is the gradient direction. The step size AI is calculated through this formula, which is the optimal step size for quadratic equations. So it's also able to get that. And then it's also able to kind of know the update rule to the list U and check for the old and new parameters. So then what it does is that it interprets all of this, and then it puts it together, right? Putting this together, it's demonstrating a method of steepest descent, a type of gradient descent to solve the linear regression problem. Instead of using the normal equation directly, yes, so that's what it says here, which gives an exact solution. Steepest descent iteratively approaches the minimum of the quadratic loss. That is correct. This is like iterative optimization. That's another name, like how you do it, because you're iterating, you're going back forth, like you're doing that. This is a common concept in optimization for machine learning, where iterative methods are used with a closed form solution. That is correct. When the closed form solution is computationally expensive or not feasible. So many times what happens is that closed forms may look very nice, but it may not be a good. So it's two things, right? One is maybe computationally expensive. The second thing is that there may be some errors in the noise and then so on, so that may not be the correct one. So maybe that's what it's also saying here. So the main concepts here are linear regression, the normal equations, and steepest descent optimization. The lecture is likely teaching about different methods to solve linear regression problems. This is amazing. I don't think O1 or even Google Gemini Flash thinking went to this extent, comparing closed form solution with iterative optimization techniques. The code example illustrates how steepest descent works step by step to find the parameters. So here is the extracted code. So it is able to extract the full code from. So it's amazing, right? I mean, this is simple OCR. But basically, what it has done is that from this, it's able to extract all of that pretty easily. So that's one other thing that it has done. And let's see what's there. So concept explained. So far the thinking part is over, the extraction part is over. Now it's going and putting things in like a LaTeX-like format. The code demonstrates linear regression solved via the steepest descent optimization algorithm and optimization technique. You have the linear model. The code generates the linear model here. Then the normal equations are derived from the closed form to linear regression. Then the steepest descent. So computing the residual using an adaptive size AI for faster convergence and using the parameters until it changes basically the stopping condition and so on. And finally, it gives the purpose. The lecture contrasts closed form solutions, example, normal equations with iterative optimization. Steepest descent is foundational for understanding more algorithms like gradient descent, machine learning. So these are the extra things it gives. That's pretty amazing. The code shows how to iteratively solve linear regression without matrix inversion. That's also amazing, without matrix inversion. So there's no inversion here, highlighting trade-offs between computational efficiency and precision. So it's like you don't actually do the inversion. You're just updating the values and kind of doing it. So this is amazing, right? So this is, I would also give this full points and like when comparing this with O1 as well as the Gemini Flash 2.0 thinking model, and I somehow feel there's no bias here. It's just the when I tried Google's Gemini, I thought that was slightly better. Maybe O1 was also better in some aspects, but this one is also like it's a kind of a different perspective, and it appears to be even more detailed and kind of and to the point as well, like kind of. So that's pretty amazing. So I just wanted to check from the code if we can get the concept, and Deepseek R1 did it brilliantly. Like it was able to get the stochastic gradient descent and iterative optimization for linear regression just from a Python screenshot. That's absolutely amazing. So one more thing we'll just do. Can you illustrate this with a simple visualization? I don't know. I did not do this with O1 and Gemini, so let's see if it can even. I don't know what to expect. Let's see what it does. So again, it's thinking, and then let's see. It's amazing. It's actually like even saying how to like do the visualization, like plotting the contour lines, and then saying using matplotlib what it should do. So let's see. Wow. So implementing this in code, create a mesh grid for slope and intercept, alternatively compute the loss, generate the steepest descent. It's pretty fast too. So that's also like nice to see. Still going on. So it's another interesting thing. Wow. Compute loss for all parameters. Maybe that's one other like thing which I think slowly people will start realizing. Sometimes it goes on for too long. Thinking models in general, they're supposed to take time and to think and then come back. But then it's like there are two sides of this, right? It's like a double-edged sword. One is, it's one on one hand, it's amazing to see how it's thinking and coming up with a solution. But then the other hand, it says this should generate the desired visualization. The contour plot shows the lost landscape. The green star is the true parameters. The red star is the final estimate. And then it says, okay, potential issues to check. So it's like, it appears that it found a solution, but then it's like, maybe it should check something, right? So it's like gone back to like, maybe I should check something here. So that's an interesting thing. Whether it's how receptive this is going to be different. So it's basically given the code. Here's the visualization that illustrates the steepest descent optimization for linear regression. So mostly they've just like they've added some more things from the original code. So I guess what it has done is that, like, I was trying to see if it can actually like generate some visualization or animation by itself. So I guess it did not do that. So what I'm going to try instead is that I'm going to copy this code, and then I'm going to try to see if it actually like gives error or something like that. So I'm just copied this code to a Colab file, and apparently I'm getting an error. That's very strange. So it says loss equals np.sum x minus y y.squeeze. So still operations could not be broadcast with 20. So let's maybe copy this error and tell Deepseek that, this is the error I got an error. But then it's like, now it's like it's going to do the thinking process again. So there are two ways to do this, right? I could have also gone through the code and then try to see if it looks okay, and then try to find the error. What I'm right now, what I'm doing is just a blind, like just copying the error and pasting it here and hoping that it's gonna just fix it. Yeah, this was faster, so that's nice. Thought for 8 seconds. It's not like the previous one, which was super long, right? The error occurs because the dimensions of x, w, and y don't match for broadcasting. Here's the fixed code for the explanation. Fix the loss function. So reshape y. So it basically asks me to like copy this, right? So what I'm going to do is that just going back here, and then so wherever the loss function is, I'm going to see if I can copy that, right? So this also said that line 38 is where the error was. So I'm going to go back to line. Okay, it's also found this error here. So I think I'm going to replace this. I think this line, the second one, is already there, so I don't need to copy that. So now just run this, and if this gives me the visualization, I'm a happy man. Okay, it did give the visualization. This is amazing. I am a happy man. So you can see here, right, this was the starting point, and then it's like it has one, it has another one, it has another one. Slowly it's kind of fallen here into the minimum. So that's great. Yeah, at least, I mean, this is what is nice to kind of have, right? It's not just explanation of the code, but if you want to build further with the code and then visualize and like see it for yourself, that's really amazing. So overall, this is pretty cool. So I'm happy with what I got so far, both the explanation of the code as well as the visualization that it did. So until next time, see you.